Welcome to the Explainer. You can think of electricity as traffic flowing through the complex roads of a circuit. So, what are the traffic laws? What keeps everything from crashing? Well, that's what we're diving into today, Kirchhoff's laws. These are the fundamental rules of the road that govern everything from your desk lamp all the way up to a supercomputer.
So, have you ever looked at a complex circuit diagram and just wondered, how on earth does the electricity know where to go? I mean, it can look like a total mess, right? A complete chaos of wires. But believe it or not, there's a beautiful, elegant order to all of it. And it's all governed by two surprisingly simple rules.
All right, here's our game plan. We're going to start with the big, universal rules that underpin everything. Then we'll jump straight into Kirchhoff's first and second laws. After that, we'll see how those laws actually build the other circuit rules you might have already memorized. And of course, we'll get our hands dirty with some practice problems before we wrap up. Sound good? Let's jump in.
Okay, so before we even mention the name Gustav Kirchhoff, we need to take a step back. We have to talk about something, well, something much bigger. It's not just a rule for circuits, it's a fundamental law of the entire universe. And it all comes down to one simple idea: conservation.
It's the principle of conservation of charge. Now, that sounds fancy, but the idea is actually super simple and really profound when you think about it. You can't just create electric charge out of thin air, and you can't make it just vanish into nothing. It has to go somewhere. Every single electron has to be accounted for. Now, burn that idea into your brain, because it is the absolute bedrock of Kirchhoff's first law.
Okay, so we've got this core idea, right? Charge is always conserved. Now let's take that universal law and see what happens when we apply it to a specific point in a circuit, a point we call a junction. Any spot where the wires split and the path divides.
And boom, that brings us right to Kirchhoff's first law, often called the junction rule. And really, it's just common sense if you remember what we just talked about. If charge can't be created or destroyed at that meeting point, then whatever amount of current flows in has to be the exact same amount that flows out. It's as simple as that.
Take a look at this picture. It's a perfect example. You've got this total current, let's call it I, flowing into that point. And then it splits. Some goes down path 1, some down path 2, and some down path 3. But here's the key. Because charge is conserved, if you add up the currents in those three branches, I1, I2, and I3, it has to perfectly equal the total current I that came in. No charge just vanishes at the intersection.
All right, let's put some numbers on this to make it really stick. Imagine 12 amps of current flowing into a split. If you measure one of the paths and see 5 amps going that way, well, what does the other path have to be carrying? It's got to be 7 amps. There's no other option, because what goes in must come out.
Let's try a worked example from a textbook. We start with 175 milliamps coming from the supply. At that first junction, 75 milliamps goes one way. So what's the reading on ammeter A3? It's got to be the rest, right? 175 minus 75, that's 100 milliamps. Simple. Now follow that 75 milliamp path. It hits another junction and splits again, with 25 milliamps peeling off. So what's left for A2? Well, 75 minus 25 is 50 milliamps. And finally, all those separate paths come back together. So what does A1 read? The grand total, of course. The full 175 milliamps all accounted for.
Okay, so law number 1 is all about conserving charge. Makes sense. Now, Kirchhoff's second law is built on the other great conservation principle in physics, the conservation of energy. And the idea is exactly the same. In a circuit, you can't just create energy from nothing, and it doesn't just disappear. It just gets transferred around and changes form.
To really get this, we need to be clear on two key terms: EMF and potential difference. So EMF, or electromotive force, is basically the energy boost the battery gives to the charge. Think of it as the push that gets everything moving. Potential difference, or PD, is the opposite. It's the energy the charge loses or drops off as it passes through something like a resistor. So EMF is the energy supplied, PD is the energy used.
And that right there leads us directly to Kirchhoff's second law, which we call the loop rule. All it says is this: if you follow any complete path, any loop, in a circuit, the total energy supplied by the batteries has to be completely used up by all the components in that loop. It's like an energy budget. The energy you get, the EMF, has to equal the energy you spend, the PD. The books have to balance.
So what do we mean by a loop? It's just any path that starts and ends at the same point, making a complete round trip. Look at this diagram. As a little bit of charge leaves the battery, it gets a kick of energy E. As it goes around the loop, it drops off some energy at the first resistor V1 and the rest at the second one, V2. By the time it gets back to the battery, it's used up all the energy it was given. The total gain equals the total loss.
So how do we use this? Check out this circuit. We've got two batteries, but hang on. Look closely at how they're connected. They're actually fighting each other. The 3-volt cell is pushing one way, and the 1.5-volt cell is pushing back. So what's the net result? A total push of only 1.5 volts. And that energy has to be spent on the resistors, which total 6 ohms. We set them equal. 1.5 volts equals the current, I, times 6 ohms. A little algebra, and we solve for I, 0.25 amps.
Now this is where it gets really cool. You've probably memorized formulas for combining resistors in series and parallel. But where do those formulas come from? They aren't magic. They are the direct consequences of applying Kirchhoff's two laws.
Let's start with series resistors. The second law tells us the total voltage drop is just the sum of the individual drops. We can sub in Ohm's law, V equals IR, for each term. Now for the key insight. In a series circuit, there are no junctions. So the first law tells us the current I is the same everywhere. Since I is in every part of our equation, it just cancels out, leaving us with the familiar formula, R total equals R1 plus R2.
Okay, what about parallel? We just flip the script. This time we start with the first law. The total current splits into the branch currents. We substitute Ohm's law again, but this time as I equals V over R. Now the second law tells us that the voltage V is the same across each parallel branch. So the V on top of every term is constant, and it cancels out. What are we left with? That reciprocal formula you've probably seen before. Both laws working together.
All right, theory is great, but the real test is applying it. Let's run through a couple of exam-style questions to see how we can use these laws to solve some real circuits.
Let's start with a classic series circuit. We've got a 12-volt battery and 3 resistors. First step, find the total resistance. Since they're in series, we just add them up to get 20 ohms. Second step, apply the second law to the whole loop. The 12-volt push from the battery must equal the current times that total resistance. A quick calculation, 12 divided by 20, and we get the current, 0.6 amps. Easy enough.
Now for a problem that needs both laws. We know 3 amps goes into a split with a 5 ohm and a 10 ohm branch. So by the first law, I1 plus I2 has to equal 3. But we also know the voltage drop across both parallel branches is the same. That's the second law. So I1 times 5 ohms equals I2 times 10 ohms. Now we have two equations, we just solve them together, and we find that 2 amps takes the easier 5 ohm path, and 1 amp takes the harder 10 ohm path, which is exactly what you'd expect.
Whew, okay, we have covered a lot of ground, from the fundamental principles of the universe all the way to solving circuit problems. So let's just boil it all down to the essential takeaways.
Here's what it all comes down to. Kirchhoff's laws aren't just arbitrary rules. They are the laws of conservation of charge and conservation of energy, just applied to circuits. The first law tracks the charge. The second law tracks the energy. If you truly master these two ideas, you can solve pretty much any DC circuit they can throw at you.
And that leads to a final thought. These laws were figured out in the 19th century, and they perfectly describe the circuits on your desk. But the device you're watching this on right now contains billions of transistors, forming circuits of unimaginable complexity. So how do these same simple laws of conservation scale down to govern a world that's microscopic, digital, and moves at nearly the speed of light? That's something to think about.